Hello everyone, I'm Fran Chadha-Day and today I'm with Frank Krauss. We're both physicists at the IPPP and I'm going to be talking to Frank about his work and his career in physics. But first things first, Frank, are you living in a haunted house?
No, it's not a haunted house. I did something really stupid. I had when we went to online teaching, I did little video clips for the students, and the my face color was very sickly green, and I thought I can't do that to the students. So I started playing with the colors, and okay, I got any hair color, but not a good skin color. So in the end, I decided to go for this black and white, very kind of oldish look, which it's a little bit like 1920s. So I think that's how we should think of me, as someone who goes for the silent movie.
It's one of the more unusual pandemic effects.
Uh-huh, absolutely. It's kind
Um,
of entertaining, though.
yeah, definitely. I think it provides variety for the
Mhm.
students as well.
Indeed, yeah.
So, Frank, onto your research. Can you tell us what the one big question that your research is trying to answer is?
Yeah, I don't think I would call it a big question like the origin of the universe or so. I think what I'm mainly concerned about is to work at a very detailed understanding of the dynamics at high energy colliders. So think of the Large Hadron Collider where we smash protons into each other, and look what happens, and up to a few thousand of particles can be created in these collisions. And I try to understand in a relatively detailed way of how to understand these collisions based on first theoretical principles. So I think the big question, this detailed understanding of particle dynamics at the largest scales.
Right. So we've got the standard model of particle physics, which is our best model for particle physics, and you're working on doing some maths from that to try to figure out exactly what happens when these particles interact to a high level of precision.
Yes, that is it. And in fact, I think the one thing that dramatically changed from about, say, 30 years ago when I started studying is 30 years ago, a lot of let me call it discoveries or work in that arena were still based on paper and pencil. And I think that has by now changed completely. We have we have so much refined our tools that a lot of the analysis is only possible with the computer. So although I'm far from being computer wizard, I mean, think of my laptop camera. Um, what I do is I pretty much program stuff into the computer to simulate it. So I think it's kind of important to realize that um, for physicists working at this kind of detailed understanding, that the tool of the trade is not paper and pencil anymore.
So you must have a very good perspective of how advances in computing have changed what we can do in physics over the past years.
Yeah, I think so, and it's kind of amusing to see how the paradigms of what constitutes a good computer has changed. When we start with what I do, memory was relatively cheap, and the central processing units were the expensive bits, and that has completely changed. And it has, of course, ramifications of what you can do. So we have much more compute power, but we don't have equally much more memory space necessarily. So to some degree, the sheer abundance and volume of data is by now more challenging than the velocity in many aspects. And that is kind of an interesting challenge because it means you have to refine your programs and how you program stuff.
Yeah, definitely. A bit like a very large scale version of when your Dropbox gets full.
Exactly. Which recently happened to me, and now I have to pay for it.
So thinking back, do you remember why you decided to become a physicist?
Yeah, I think I did. I mean, in high school, I liked maths and the sciences, and the more mathsy, the more I liked it. So I started studying both maths and physics, which in in Germany where I did my undergrad, it was like a dual study, and you had to take significantly more lectures. And at some point, I realized that I like the physics lectures much more than the maths lectures. It felt to me, it's maybe the wrong word, but maths looked a little bit more sterile. And I found the challenge of trying to describe nature in mathematical terms. I found that much more entertaining, much more challenging. I don't know what the right word is. It was just, yeah, it felt better. And I got more kicks out of it, simply put.
And over the course of everything you've learned or discovered in your career, do you have a favorite physics fact?
Yes, that it works. It sounds completely silly, but the sheer fact that it works, I think, is quite amazing, and I think it's quite astonishing how far we could push it. I think that is it's something that we take that we take as a given, but if you think in a wider context, the level at which we understand the dynamics of the universe or the dynamics of particles at the highest scales and smallest distances, that is quite amazing. And I find it absolutely crazy that we can go over 20, 30, 40 orders of magnitude and the same rules, the same principles hold water. And for me, that's nothing short of a miracle.
Yeah, I think you're absolutely right. It didn't have to be that way, right? We do take it for granted.
Exactly. Yeah. I mean, we could still live in some medieval age where everything is a miracle, and where science, you know, is mainly concerned in turning muck into gold. And the sheer fact of how we do science in physics, I think, is also, I think it's quite exemplary, and it's a good show for humankind in a way. It tells us how good we could be in using our best instruments.
Yeah, absolutely. So you've described how your research is trying to generate more precise predictions for the LHC using computer simulation. Can you describe what that looks like day to day? What's a typical day in your job?
Well, it's by far not as glorified as it sounds. So at the moment in pandemics, yeah, at the moment nearly everything goes, of course, via Zoom or Teams or Skype, so multiple platforms. And I think at the moment I average of the order of 5 hours in Zoom or Skype or Teams conferences. And it's a wild potpourri of very different things, from teaching to teaching administration, to supervision of students, to genuine boring bureaucratic stuff. And I think that takes a large part of my working day. I would say easily half or more. And in the so if you ignore that for a moment, because it's not fun to talk about that really. The rest is quite often filled with me sitting in front of my laptop and trying to program something. And in fact, programming means looking for the mistakes I did just the day before, which, which also sounds, it sounds horrible, but actually it's very gratifying, and it's very gratifying to then in the end you run your program and produce the right results, and or it describes data, and that is yeah, that is the fun part. That, and probably supervising research students is, I think, for me, is the most gratifying part of the job.
And over the course of your career, what do you think has been the highlight? So it doesn't necessarily have to be your best discovery, but it could be. But what's been the best bit for you?
The best bit for me was, so in terms of, say, development of the field, for me, the discovery of the Higgs boson, no question, was amazing. We kind of, as a community, we kind of expected it and we downplayed it. But if you think about it, it's a mechanism that was proposed 50 years before it was measured in a way in reality. And in terms of knowledge development of humankind, I mean, if you take a measure like how many books have been published from 1960 to 2010 within the 50 years, it is much more than in this 50 years. More books have been published in the world than all the rest of humankind together. So we have something in the beginning of this incredible explosion of knowledge, or somewhere in the middle. No idea how you want to, put it in temporal perspective, but we have this proposal of how particle physics really works, and 50 years later we switch on this collider and we find it, and I think that is absolutely astonishing. So in terms of discovery, yeah, I think that's the biggie. For me personally, well, I developed one or two nice little tricks of how to make these simulations run a little bit better. I developed, I think I think that was, in terms of, achievement, that was kind of nice. But personally, for me, my biggest achievements actually is how well some of my students do. So I think I can say that some of my former students are much, much better physicists than I am. And I'm quite happy that I maybe helped them a little bit. And I think that, I think that makes me kind of proud. Yeah.
Nice. And looking to the future, what is the discovery you're most hoping to see in your lifetime? Whether that's something you discover or by somebody else.
I hope to find something like elementary dark matter. That would be really cool if we would find it, because that would connect our super duper precise knowledge of particle physics with something that shapes what the universe looks like. And I think that would be really, really nice. It would manifest our ambition to span everything from the smallest to the largest. I think that is something I would really like to see. Yeah.
And can you give a one paragraph explanation of what dark matter is for anyone watching who hasn't heard of it before?
Okay. So if you look out of your window or inside your house, unless of course it's black and white, but because then it wouldn't be so entertaining. But pretty much all the matter you see is light, in the sense that it interacts with light. It can emit light, and therefore you can see it. Maybe it radiates light at very short frequencies or very long frequencies, so the eye cannot see it, but we see the interaction. And dark matter now is a part of this matter that we cannot see, and it pervades the universe. Now the thing is, the interaction of dark matter are probably mostly gravitational, or they're very weak with anything else. But this gravitational interaction actually shapes the universe, in the sense that it forms clumps in which matter can cluster together and form stars and galaxies. So we have indirect evidence for this mechanism of how galaxies and stars form, and what the role dark matter plays in it. But we have no real idea what it fundamentally consists of. We only know what it does not consist of, namely all the stuff we see in our daily lives. And I think that's kind of an interesting one, that we have indirect evidence for something, and now we look for it, and we have a number of ideas what it is not, which is probably not enough. But hey, so finding something that fits the bill would be really exciting.
Yeah, I agree. That's I think the identity of dark matter is really one of the biggest mysteries in our current kind of paradigm of how we're describing the universe.
Yeah, I think that would be a biggie. On a more, like, let me call it, secondary level, the one thing that I would probably, but that's more because it's my little topic. The one thing that I would probably like to see is a more quantitative understanding how quarks form protons. We kind of know it qualitatively, and we can put it into simulations, but doesn't feel very satisfying, our level of quantitative understanding at the moment. So understanding a little bit more there would be fine as well.
Do you think, this is really just for my personal interest, but do you think there's likely to be a step change in our understanding of that? Or do you think the formation of protons from their constituent quarks is just not possible to understand in a mathematical way, however clever you are?
I generally don't know. I generally don't know. If you listen, so my perception, and that's probably completely unfair, my perception is that the efforts in lattice QCD, it always feels like it's just around the corner, but it never really is. So it's entirely possible that this turns out to be something very similar to nuclear fusion, always 30 years ahead. You know, that it's a bit of a bad joke. So yeah, I just hope there is some clever idea of how to put a proton into the computer, and it just happens.
Yeah, one of the things that always really strikes me about actually a lot of theories in physics is that often we're able to write down equations that we think describe the universe, but then actually solving those equations is incredibly difficult. You know, the universe can clearly solve them, but we can't.
Yeah. Yeah. On the other hand, I think the one thing that completely gets me with physics is it sounds completely cheesy. It's a little bit more than just science. I think it's a school of thought, and so I think the way we approach problems in this funny mix of writing down equations and hoping that we can solve them with whatever means, either paper, pencil, or with big computers on one hand, and then looking at data and see if our hypothesis is justified, and then to refine. I think that is it's a very powerful concept, and I think this is the thing I over time learned to value more and more about physics. That it's a school of thought. It's a very, very good way of how to think, how to approach a problem, and I think that is something that I wouldn't miss for the world.
Yeah, I think this goes back to what you said before about your favorite physics fact, that it's pretty astonishing that this way of thinking actually works, that we can write down these often relatively simple equations that turn out to describe everything.
Exactly, yeah. I think it's also for I mean in a wider perspective, if you look at it, we train students, undergrad level, postgraduate level. Many of them learn this way of thinking, maybe hopefully by example for us, and not just because we drill it in them, but more by good example. They can do amazing things outside physics as well. So it tells me that it tells me something about the value and the validity of this way of thinking as well.
And the last question is, what are your hobbies and interests outside of physics? What else do you like to do?
Before the pandemic got us, I played tennis 2 or 3 times a week, and that was really nice. Because you just go and you hit a ball, and it's it's great. Other than that, I have 2 boys in 11 and 14. So playing with them, and okay, the 14-year-old by now, for him, I'm a boring old person, I think. But for the 11-year-old, board games, building Lego stuff, or so, that's the kind of stuff which, whether I like it or not, becomes a hobby.